Good morning. Let us see today unharmonic oscillator. What is unharmonic oscillator? We have earlier studied simple harmonic oscillator. Okay, all real molecules do not obey the laws of simple harmonic oscillations. All real molecules, the stretching, compression are not elastic. They obey unharmonic oscillator. Okay, so we have earlier studied simple harmonic oscillator. Please watch the lesson. Now, the simple harmonic, in the case of simple harmonic oscillator, the potential energy expression in simple harmonic oscillator, the potential energy expression is equal to 1 by 2. E is a function of, the potential energy is a function of R, 1 by 2 kx square. This is a parabolic equation. On plotting this, a parabolic curve is obtained. Plotting this using this potential energy function. Okay, E energy versus potential energy. Actually, this is potential energy VR only with respect to as a function of R, as a function of internuclear distance. See, this is the what is a molecule? Two atoms are connected by a spring. This is the equilibrium bond distance or equilibrium. At R equilibrium, the potential energy is minimum. The potential energy is the lowest. Okay, see, the potential energy is minimum, 0. And when you stretch, the bond length increases. Therefore, the potential energy increases. Similarly, when you compress, on compression, the potential energy, what happens there? Or decreases, potential energy increases. So this is the potential energy diagram for simple harmonic oscillator obtained using this expression. We have earlier studied what is K is called the force constant obtained by using Hooke's law. X equal to R minus R equilibrium. That is, for example, R minus R equilibrium. How far it is away from the X is a measure of how far it is away from the equilibrium distance. X. Okay. Now, by using this potential energy operator, by using this potential energy expression, the Schrodinger wave equation for simple harmonic oscillator can be solved to obtain the energy levels. To obtain the energy expression, from the energy expression, the energy levels are obtained. From the energy expression obtained by solving the Schrodinger wave equation, this is obtained, the energy expression for simple harmonic oscillator. The energy levels are obtained by using this expression and the spectrum is obtained by using this energy expression. Remember that in terms of this is EB equal to E plus 1 by 2 h nu. Okay, the nu where nu is the fundamental frequency. Where V is the fundamental frequency of vibration, nu is where V is the vibrational quantum number 0, 1, 2, 3, etc. This is in terms of wave number. Vibration spectroscopy or IR spectroscopy are expressed in terms of wave number. Therefore, nu what? The conversion, how to convert this, I was shown earlier. Please watch the lesson. Now, the selection rule for simple harmonic oscillator is delta V equal to plus or minus 1. Okay. Therefore, 0 to V equal to, this is V equal to 1, you can obtain V0 and you can get E1. Energy for ground state, what is the energy for ground state, what is the energy for the first excited state, what is energy for the first second excited state, etc. Okay, so you can substitute V equal to 0, this energy is obtained. V equal to 1, energy is obtained. Okay, now because the energy gaps, you see, the energy gaps are constant. Therefore, only one spectral line is observed in the IR spectrum. The vibrational energy levels, actually, the transition occurs, the vibrational level transitions occur in IR region of electromagnetic spectrum. Therefore, vibration spectroscopy is called IR spectroscopy. Why? Why vibration spectroscopy is called IR spectroscopy? The vibrational level transitions occur in IR region of electromagnetic spectrum. Okay. Now, see where nu is the fundamental frequency, fundamental oscillation frequency, fundamental vibration frequency. This is the wave number in terms of your nu. Nu is obtained, fundamental frequency of oscillation is obtained by using this expression. We have studied 1 by 2 pi square root of k by mu. Okay. It is converted to wave number by using this expression. Similarly, you can take it out here and the force constant is obtained. Okay. Now let us see. This is the expression, potential energy expression used for simple harmonic oscillator. All the molecules are, all the real molecules are not elastic. So Morse defined a potential. Morse derived a potential to fit the curve, to fit the experimentally obtained curve. This is the experimentally obtained curve. This is the theoretically obtained curve. This is the experimentally obtained curve by using Morse function, Morse potential. He obtained this potential energy expression for unharmonic oscillator. This is the potential energy expression for simple harmonic oscillator. This is the potential energy expression for unharmonic oscillator. The potential energy is a function of R. Okay, if you stretch potential, if you stretch a bond, the potential energy increases this way. If you compress, so bond length decreases, the potential energy again increases. At R equilibrium, the potential energy of the molecule is very minimum. Okay, V is a function of distance equal to D equilibrium 1 minus E A x whole square, where A is a proportionality constant. D equilibrium is the dissociation bond energy, that is spectroscopic dissociation bond energy, dissociation energy, and D, it is how it is obtained. I have shown here. D naught is the experimental dissociation energy. When you stretch, for example, at lower vibration levels, the two obeys simple harmonic oscillator. See, up to this, the energy gaps are constant, equal. Energy gaps are equal. Only at higher vibrational energy levels, at higher vibrational energy levels, okay, they deviate from simple harmonic oscillator. They deviate from simple harmonic oscillator, because when you stretch more, the bond will break. See, this is this point, the bond will break. At this quantum number, for example, nu equal to 9, so nu V equal to 9. At what quantum number the bond breaks? Okay, it can be calculated by using this expression, and so this is the potential energy expression obtained by Morse for unharmonic oscillator. This is the potential energy expression for simple harmonic oscillator. Similarly, by using this potential energy function, the Schrödinger wave equation was solved to obtain the energy expression for unharmonic oscillator. This is the vibration energy expression. This is the vibration energy level expression for unharmonic oscillator. This is very similar. You see V plus 1 by 2 nu bar minus V plus 1 by 2 whole square V nu bar Xe, where nu bar is the fundamental absorption frequency or wave number. Xe is called unharmonicity constant. If it is equal to 0, then it becomes simple harmonic oscillator. If Xe is equal to 0, then this term is equal to 0, then it will become simple harmonic oscillator. Okay. Now from this is the experimental D equilibrium. This will be D equilibrium. This will be here, and this will be here. Higher value D equilibrium minus D naught. Okay, this is experimentally observed, and we can calculate the fundamental frequency or fundamental wave number. Now, the selection rule obeyed by simple harmonic oscillator. The selection rule obeyed by simple harmonic oscillator is delta E equal to plus or minus 1, therefore 0 to 1, 1 to 2, 2 to 3. You will all, the energy gaps are constant, therefore only one spectral line is observed, whereas here the selection rule follow this delta V equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. Okay. Now, let us see, for example, here, therefore, 0 to 1, 0 to 2, 0 to 3, plus 2. For example, 0 to 2 means plus 2. 2 to 0 means minus 2. The selection rule used is minus 2. Therefore, you have 0 to 1. This is the fundamental frequency. And 0 to 2. 0 to 2 is 2 nu bar. First overtone. Okay, one step ahead. Not one step. You are going one step. Not here 2 steps. Okay, therefore 2 nu bar, first overtone, 0 to 2. 0 to 2 is first overtone frequency, 2 nu bar. Okay, and the 3 nu bar is the second overtone. For HCl molecule, the observed spectrum is this. Okay, now let us calculate the fundamental absorption frequency, fundamental energy difference. Okay, delta E1. Let us E equal to 0, you substitute. E equal to 1, small e 0, and you put 0, 0, and then E1. I have given the procedure in the next slide. You can see, therefore, on calculating the delta E. Delta E means, delta E1 means E1 minus E0, therefore nu bar 1 minus 2xe centimeter inverse. This is the nu bar is the fundamental absorption wave number. This is more intense. This line is more intense because V equal to 0 at room temperature, the ground state is more populated. The ground state is more populated. Therefore, there will be high probability of transition. Therefore, this peak is more intense. They will ask sometimes. And now 0 to 2. 0 to 2 is called, they are called overtones. There is overstepping. Okay, you go 2 steps ahead. It is not possible. So overtones, it is possible in the case of unharmonic oscillator. It is not possible in simple harmonic oscillator because of inelastic vibration in unharmonic oscillator. Delta E2, similarly you can calculate same 2 nu bar 1 minus 3xe, and delta E3 0 to 3 transition, and 3 nu bar 1 minus 4xe. Similarly, you can calculate for 0 to 4 third overtones, etc. What are called overtones? Overtones are transitions. Overtones are IR transitions arise due to the 0 to 2, 0 to 3, 0 to 4, etc. Okay, 0 to 2, the transition from the IR transition from 0 to 2 is called the first overtone. The transition from 0 to 3 is called second overtone, and etc. Okay, they have small intensity. For example, it is of small intensity because it is very difficult. The probability from 0 to 1 is higher. The probability for transition from 0 to 2, 0 to 3 are decreasing. Therefore, the intensity decreases with increasing overtones, with increasing number of overtones. For HCl molecule, there are several lines of time. For example, this is fundamental frequency. I have told earlier. This is overtone, and also there are hot bands appearing in the IR spectrum. What are called hot bands? Hot bands arise due to vibrational transition from 1 to 2. Usually 0 to 1, 0. The transition occurs from 0 to 1, 0 to 2, etc. Now, in hot bands, the vibrational transitions arises from 1 to 2, 1 to 3, or 2 to 3, V1 to 2, V2 to 3. These are called hot bands. How it is identified? For example, when you at room temperature, the ground state is more populated. V equal to 0 vibrational energy level is more populated. When you increase the temperature, what will happen? The molecules will jump to V equal to 1. Therefore, at high temperature, V equal to 1 is more populated. Therefore, 1 to 2 transition occurs of considerable intensity. As we increase temperature further, then 2 to 3 will occur. 2 to 3 will occur. 1 to 2 also will occur. The intensity increases with increasing temperature. Then they are called hot bands. They are not of high intensity, but with increasing temperature, it increases. The intensity increases. I have shown the procedure for this, and also how the conversions are carried out. Thank you for watching.